Okay, so now we're going to be diving into static friction, and we're going to split it over 2 lessons because static friction is probably the trickiest force that you are going to draw in AP Physics 1 or AP Physics C Mechanics. It is the trickiest one to analyze. So the key part here is static friction is this reactive force. So we talked the last time about kinetic friction. Kinetic friction is when it's rubbing against the surface, but static friction is one of those cases where there's not a formula defined, it's reactive. So let me kind of give you kind of an illustration. So I always illustrate this by putting, say, my calculator on my hand like this. Okay, so right now, if we just draw the free body diagram, we have a normal force from my hand upward, we have gravity pointing downward. Now, this is the tricky thing because there is a coefficient of static friction between my hand, human skin, and this plastic bottom of my calculator here. But at this point, there's no horizontal forces. If I keep my hand pretty level here, pretty level and flat, there are no horizontal forces at this point, right? And so you want to say like, well, there's a formula, this mu times normal force, right? But that doesn't exist right now, or that there's a number from that because there is a non-zero normal force and there is a non-zero coefficient of static friction. However, there is no static friction acting right now. It's not until I push my finger a little bit. Okay, I push my finger a little bit. I push on here. Now it's not accelerating to the left. Why is that? Because now the static friction is beginning to increase. It's matching, and because the acceleration is 0, it's matching the force that I'm applying. So I'm applying a force this way, right? But the static force is reacting and applying this way. So if I apply 0.1 newtons this way, the static frictional force is 0.1 newtons the other way to keep the net force 0 because the acceleration is 0. And so I can increase it. So now I'm 0.2 newtons or 0.3 newtons or 0.4 newtons. And again, it is not accelerating, right? So the static friction's reacting and keeping everything so that the acceleration is going to be 0 until I get to a certain point. I put enough forces here and then it begins to slide. And so that threshold, the back to our notes here, the threshold by which it will then go from static to kinetic friction. That's what we have a formula for. We have a formula for the maximum static friction, which is mu s times Fn. This is not what the static friction is. This formula, unlike kinetic friction was the coefficient of friction times the normal force. Static friction, that tells you just what the maximum frictional force would be before it will begin to slide and rub against the surface. Okay, as a note of fact, coefficient of static friction is usually greater than the coefficient of kinetic friction. It's similar in kinetic friction in the sense that it is based on the property what the two materials interacting are made up of. So because it's not sliding, the hardest thing to figure out is what is the direction of the static frictional force, okay? Because there's not actually sliding. There's not actually any motion to go against, right? And so there's 2 ways that I suggest that you look at it. Okay, option 1, this is the most robust option, but this is sometimes really tricky. But the easiest way to think about it is to pretend that there were no friction. Which way would the object slide? Okay, so like in the case of my calculator here, if I push this way and there were no friction, it would automatically just slide to the left. And so then the static friction would prevent that hypothetical sliding from occurring. Okay, this is probably the most robust option, but again, can be tricky until you have a lot more experience with different scenarios to think about, right? So another option to identify the direction of the acceleration is to look at the net acceleration of the object as a whole and to see which way the force would need to be to make that acceleration. Okay, now I don't say acceleration 0. Don't confuse. Because there's static friction does not mean that the acceleration is necessarily 0. Okay, so I want to get that very, very clear. A lot of time, like in the case of my calculator, yes, the acceleration was 0, but remember, identifying the acceleration is different than like what's actually happening. So you just identify which way the acceleration would have to be, and it might be 0, and then the static frictional force would be necessary to make that happen. Okay. Now, this doesn't always work. There are some scenarios, this is not as robust, even though this is something easier. So I know this is a little bit tricky because you would identify the acceleration, then draw the free body diagram in terms of our steps. But that is sometimes necessary to think about what the acceleration is happening, and thus the frictional force, static friction, would be necessary to make that acceleration happen. in that instance. Okay, and so we'll look at both options as we go through a few examples here, or over time as we do more and more advanced problems. Okay, so let's take a look at this first one here. We have a contestant pushing this block across a frozen length, very similar to the kinetic friction. We have the coefficient of static friction, coefficient of kinetic friction. Draw the free body diagram and identify the static friction. Oh, I didn't write the scenario here. Is the block is not moving. So identify the direction of static friction when the block is not moving. When the block is not moving. Okay. So he's pushing on it and the block is not budging. Okay. So let's draw a free body diagram here. So we're going to have gravity acting downwards. All right. We're going to have a surface touching it. So that's going to exert two forces, normal force and the frictional force. Unclear at this point. So the frictional force would be down in, oh, sorry, not the frictional force. The force they're applying is down and to the right. But we still have to consider the static frictional force here. Okay, so here's the way we look at two options. Option one, if there were no friction, then the net force is going to be to the right because there's no other forces. So we're just imagining there's no friction. Then this thing would accelerate to the right. But because the block's not moving, we got to oppose that. So that means the frictional force has to oppose that sliding, that imaginary sliding, and that would be the static frictional force there. Okay, second option. Which way is the acceleration? If it's not moving here, the acceleration is 0, and we need a leftward force to counteract the rightward force to make the net force 0 to give us 0 acceleration. Both options would tell us that the static frictional force would have to be to the left. Okay, kind of see how that works. Let's take a look at this one. Same scenario when the block is not moving. Okay, again, we're going to draw the free body diagram. So we're starting with easy examples because I want you to understand how it applies to easy examples so we can then apply it to hard examples. What's touching it? We got this F up at an angle. What else is touching it? We have a normal ground, normal force here. And this surface can also exert a frictional force. Now, let's think about it. Option one way to think about it, if there were no friction. So just imagine we're done with our free body diagram because nothing else is touching it, right? If this was it, this thing would accelerate to the right, but it's not accelerating to the right. The block's not moving. So that means the static frictional force is going to the left. Or the second option, again, the acceleration would be 0 in this case. Okay, if the acceleration was 0, we would need a leftward force to counteract the rightward force that we're getting from F. Okay. So that's kind of the idea there. Let's look at another one. Block A is being held in place with an applied force F. Assume the block has a mass of 6 and coefficient. Draw a free body diagram. So it's held in place. So again, similar acceleration is 0 in this case. But let's go ahead and just draw the free body diagram. We're going to have gravity. What's touching it? We have this F applying to the right. What else is touching it? The wall is touching it. That exerts a normal force perpendicular to the surface to the left. And this surface might also exert static friction. So let's think about option one. Option one says, if there were no friction, what would happen to this guy? Well, there's a net force downward. He would just fall to the bottom. He would slide downward, right? So to oppose that, the static friction must be pointing upward, parallel to the surface, right? And perpendicular to the normal force. So that's where the static friction is going. Other option two, is to think about, well, I know the acceleration is 0. So the frictional force has to be pointing upward to counteract gravity to make the net force 0. Okay, so that's how we do identify at least the direction of static friction, which is probably the trickiest part when you're drawing that free body diagram.